Okay, welcome to our presentation on sensitivity, specificity, and the ROC curve. We are the seniors. So just to give kind of a brief overview of sensitivity, basically it's the true positive rate. So we calculate sensitivity by taking the number of true positives and then dividing by true positives plus false negatives, which is in sum the total number of known positive cases that we have. So this is really useful for identifying like false negatives when they're dangerous. So for example, we'll get to an example on the next slide, but in the case of something like cancer or say we're going fishing in a pond and we're trying to catch like rare fish, which are positive cases, sensitivity would be how good our net is at catching those rare fish. So just to look at an example, so if we're administering a test for cancer, for a rare type of cancer, and we know that 200 people have this rare type of cancer, we can test the sensitivity of our test by administering the test and then seeing the rate of true positives and false negatives, and then just doing the equation like we talked about in the last slide. And that should be able to provide us with our rate of specificity.
So apart from sensitivity, we have specificity, which is the ability of a test to correctly identify negative cases or the true negative out of all the negative instances. So basically, it measures how well a test can avoid false positives, because false positives, especially in like a medical example, you don't want to be looking at false positives. The formula for specificity is the true negatives divided by the true negatives plus the false positives, and a high specificity reduces false alarms. It's very crucial in medical testing, fraud detection, and classification models where false positives have significant consequences. And it's also used in conjunction with sensitivity for balanced model evaluation, because sensitivity is seeing how many true positives are there, and specificity is seeing how many true negatives are there. So you really know what is going on with your data set. And to look at an example, what if there is like a bank, right? And this bank uses an AI model to detect any sort of fraudulent transactions. So out of 10,000 actual transactions, the model correctly identified 9,800 as non-fraudulent, and these are known as the true negatives, but it incorrectly flagged 200 transactions as fraudulent. So those are the false positives. So using the equation, we see that this model has a 98% specificity rate, which means that it's highly effective at recognizing legitimate transactions and minimizing false fraud alerts. So this ensures that customers experience fewer unnecessary disruptions. So you can see how useful specificity is.
Yeah, just to look at kind of comparing sensitivity and specificity. So in the case of sensitivity, we're basically trying to identify like what are true positives, and in the case of specificity, we're trying to identify what are false positives.
So a receiver operating characteristic, or ROC curve, is basically a graphical representation of this binary classification. And on this curve, the x-axis plots 1 minus specificity, which is known as the false positive rate, and the y-axis plots sensitivity, which is known as the true positive rate. And the AUC, or the area under the curve, can tell us how effective the test is. For example, if the AUC is equal to 1, it would be an ideal or perfect test. If the AUC is equal to 0.5, it would be equivalent to random guessing. And if the AUC is between 0.7 and 0.9, that would indicate medium to strong discrimination. And we can see an example of this, for example, in the scenario that we're evaluating a medical diagnostic test for breast cancer. Sensitivity would measure the proportion of actual breast cancer cases that test positive, and specificity would measure the proportion of non-breast cancer cases that test negative. And on the graph on the right, you can see the blue point on the very left top corner is an example of a perfect classifier, and hence the blue curve would be most ideal because it recognizes that the test is highly effective. The yellow curve is closest to the red dashed line, which is our 0.5. So that means it's the closest equivalent to a random guessing. So our optimal cutoff would be the most effective point based on the clinical diagnostic test, and the point at which specificity and sensitivity are most balanced. Here are a list of our sources, and thank you so much for listening to our presentation.